in my slides. So the first thing we want to talk about is motivation. Why am I doing this? So, there's like this sort of sentiment that like as AI systems get larger and larger and more powerful, they start to become these sort of like safety critical systems. And in most safety critical systems, we have early warning systems. And so like my favorite example comes from nuclear engineering, where like your reactor pressure vessel that really contains the nuclear reaction, it can undergo a phase transition into this thing called embrittlement, where essentially the temperature, these things need to operate at a certain temperature, and if they're too cool, they become very rigid. And at some certain point, from essentially like nuclear interactions with the metal in the sort of reactor containment vessel, you can get essentially like little nodules forming, and these give a place where sort of cracks can form. And so they sort of lower the embrittlement temperature, or they raise the embrittlement temperature, sorry. And so like when they undergo cooling, you can get cracks forming. And so what nuclear engineers will do is they'll estimate about the lifetime of these sort of reactor pressure vessels, and how long they'll go without sort of entering this embrittlement thing. But like, you really don't trust that. Like, you aren't going to go, you're not going to, if somebody tells you, oh, I guarantee you this won't fail for 100 years, like, and they're just like, so we're not going to monitor it, we're just going to let it run. Like, that's a terrible, terrible idea. So what you do is you monitor it while it runs. And one of the ways they do this, a very modern way, is with like acoustic emission sensors. Because as you start to get this sort of like a lot of these little nodules forming, kind of cause like these microscopic vibrations in the metal. And these things can tell you that this thing's starting to become brittle. So, this sort of system exists in all kinds of other things, structural engineering, blah, blah, blah. So like, in my opinion, we should probably have something like that for AI. Like, it would be kind of useful if we're going to actually say that we're taking safety seriously in any meaningful way. So like, cool, I want to do that. What's on my next slide? So like, the motivating problem is for this particular work is sort of how do we detect emerging capabilities and behaviors during training before they actually solidify. So this means, I really like that this got formatted in black and you just can't read it at all against the background. So there's sort of these three things, that like kind of matter for this, where we want to talk about phase transitions, which in this lingo is sort of capabilities that emerge through qualitative structural changes in model parameters. And then we sort of want to look at early detection. So the thing, for various reasons, is can we see precursors in loss fluctuations before the capability fully forms? And then the other thing is interpretability, or can we understand what is changing, not just when a change occurs? Now, in this talk, one of the things that I didn't focus as much on the interpretability as I probably should, and I kind of regret that because I was really excited about early detection. But we can talk about the interpretability and stuff as well. So I'm going to talk about early warning signs in physics. So for most people here, I figure are familiar with the standard thermodynamic free energy, just the log of the partition function. We have some control parameter theta, which I realized before doing this talk. In the next slide, I changed it to alpha, which is pretty cool of me, inconsistent. So the first thing is we need to talk about first and second order phase transitions. And technically there are phase transitions of every order. You can have infinite order phase transitions and they're super cursed, but like whatever, none of those exist, and we're going to pretend that like everything's good. So the first like sort of nice phase transitions in some sense are second order, because the free energy and its first derivative are continuous, but the second derivative jumps. So essentially what you can see is like as the phase transition is sort of starting, the landscape like prepares that this transition, so you get precursors that are observable. And so like an example of this is something where like you're at some basin like this, and you change some control parameter, and so it starts to flatten out, right? Like it gets flatter, and oh yeah, my drawing's really good, it's sick, and flatter, and then eventually it's flat, and then it sort of starts to dip down, and this is sort of like where you kind of get this like phase transition, because then it kind of goes boop down here. But you can sort of see the precursor because things start to flatten out. And this is very nice. But then there's first order transitions, which are sort of, in some sense, like defined by the fact that I can't like see any precursor. They just happen. So
alpha is your control parameter.
Yeah, alpha is just like some thermodynamic control parameter. Like this is like definitional.
Why is this transition? Like you won't get Like you don't have to be at a minimum.
This is just the definition. Like this is like a standard thermodynamic definition of a phase transition.
Yeah. But like what you're drawing there looks more like you're drawing an order parameters where you get some inverse.
Yeah, I mean, this is because your control parameter is like an order.
I see. Wait.
So, you have your first order transitions that are not detectable. So when you have the second order transition, you have these things that we call early warning signs or critical slowing down, because at the second order transition, the second derivative approaches zero continuously as your control parameter approaches the critical value. And this produces observable kind of gradually diverging precursors. So some of these are relaxation time, because like if you're in the basin and I kick you and you're away from a phase transition, you will pretty quickly just go back to the bottom of the basin. But as it starts to flatten out and I kick you, you'll take longer and longer to go back. So this is like a very common one. The other things to look at are variance of fluctuations and autocorrelation time. The problem is that none of these hold for first order phase transitions. Now, the nice thing though, is there's a particular kind of first order phase transition, which I technically can't really detect it, but I can do something that's almost as good, which is nucleation. So when nucleation happens, essentially you have imagine you have some chemical reaction. So this is like crystallization, and somewhere in the reaction you have through thermal fluctuations, things will sort of couple together and break apart, and with some sort of probability, enough of them will couple together that it becomes stable, doesn't break apart, and then things very rapidly sort of attach onto it and you get crystal. So in practice, this is really hard, but in theory, you could detect the formation of the critical nucleus if you had perfect white box data. Because you could just look and be like, okay, well, I see that this thing has become ordered in some way, like the entropy has decreased, blah, blah, blah. You could detect it. Now in real sort of physical settings, you can't do this, but deep learning, not a real physical setting. So we get very good white box access to the model. And so this isn't really this isn't really early detection. So you're sort of just detecting the seed of the transition where things form, but good enough. And for these purposes, I'm going to call it early detection. Now, an important point that I think always gets brushed over and is actually kind of important, which is that deep learning is a dynamical system. It's not a thermodynamic one. So transitions are not thermodynamic transitions. They're metastable state to metastable state transitions. But the language still kind of applies, if you want to, we can still define something that's a free energy where you have the loss, and you have something like a configurational entropy, the parameters nearby that aren't that don't give you a model that's drastically different from your own. And so this means that we kind of have to think about what we mean when we talk about first and second order phase transitions in deep learning, because we don't really have the classic sort of free energy surface most of the time, because we're not at equilibria. So one of the ways to see this is the second order is sort of it's this sort of broad kind of flattish loss region where there's lots of parameters that give you a very similar model. And here you SGD noise drives exploration. And so gradually a subset of directions might reinforce. And so curvature increases, you can imagine you're sort of entering a tunnel and the curvature on the walls increases. And then eventually this sort of locks in. So this admits early warning via fluctuations. And so the other type is this sort of first order transitions, which I call a river valley landscape. And so there's been some research into things like this. And if you're familiar with DLNs, silent alignment is kind of like this. So there's you have some walls of a river valley, and there's some path along the bottom you want to follow. And so as you go down, you kind of lock onto this bottom part and you go straight down. So this is kind of a first order phase transition because this bottom of the valley is like an entropic barrier. It's only a small portion of parameter space, so you need to find it. This is very nucleation-like.
I don't understand the difference. Maybe can you draw a picture?
I can do my best. I can't draw in 3D very well. But the idea is sort of if you, so imagine you have something that you're up here, and so we're looking at a 2D cross section, and imagine that this slopes very gently down like this. Mm-hmm. So a first order phase transition would be something where you come down this hill, like you go do, 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 and you end up here. And at this point, you sort of locked on to this direction. And so your system, it might fluctuate around this basin a little bit, but it's primarily going to start descending this way. And so this is like the critical nucleus forms, because it forms. This is what happens when it hits the bottom, and then it amplifies down this direction.
Wait, and this direction is not a south, but it's an axial gradient.
It's something like this. It's like this sort of river valley. It's really hard to sort of draw intuitions about what high dimensional spaces look like. But this is sort of this is kind of what silent alignment does. And this is like a thing that explains why warm-up stable decay is necessary for training large models. Phenomenologically, it agrees with this. And so a second order one is sort of like, if you're top-down view, like you're here, and you're in some very wide basin, and then you sort of start to enter something like this narrow bottleneck, because as you increase this, the sort of entropy decreases. So this is sort of more like a second order, because kind of as you approach that, you sort of have this continuous transition. And so it's sort of trying to put this picture that you normally paint in the free energy landscape into something that's actually the loss landscape, which is more like a potential energy landscape. So the language has to be somewhat different. So now I'm going to introduce this thing called the 2 data point reduced density matrix. Now technically, it's not a reduced density matrix. You can make it into one if you're wondering, quite easily, but it's just more natural not to do that for various reasons, but we're going to ignore that. So if we want to do early detection, what should we measure? And we sort of talked about this, right? We want to look at these sorts of fluctuations in some way, right? And so second order, these fluctuations sort of start to increase in some sort of continuous way. And for first order, they sort of jump very suddenly. So this is kind of what we want to measure. So if you want to measure something like this in physics, you might look at something like a per site Hamiltonian. So if you have some lattice model and you look at for each spin in this lattice, you look at the average, sort of the energy at that site according to the connections it has. And then you vary the sort of strength of the connections. And you can sort of figure out how this fluctuates. You sort of use this to study how things co-fluctuate together. But we don't have a per site Hamiltonian, but we have something that's very natural analog, just per sample losses. So each sample's loss responds to parameter changes, if the loss on a sample changes, it is definitionally changing because you've changed a parameter in the model. So when the model undergoes structural reorganization, groups of samples are affected together, so their losses will co-fluctuate. So the kind of formal definition of this, and as you noticed, I haven't put that much math, really tough math up here because I don't think it actually helps understand this picture at all. But the way that we define this is we just have this covariance matrix, and the entries are essentially you have the per sample losses on some sample I and some sample J, and then you have some probability distribution about your choice of parameter. So you have some parameter and you're I have some distribution of points about this guy. And then I see how these guys fluctuate together as I sort of just perturb my parameters. Very simple, right? The problem is sort of that this is in high dimensions is really not nice. And computationally not particularly tractable. But it turns out if you're like me and you're willing to do just the dumbest thing you can think of, you can do something about this. So I do this thing that I call the dynamical 2RDM. So instead of bothering with this Gaussian perturbation or doing Bayesian posterior sampling or some giga-chad shit, whatever you think is the right way, instead I just go okay, I have some set of n samples that I care about. And at regular intervals in training, I'm just going to compute each sample's loss, and then I'm going to maintain a sliding window of loss vectors. So at every time step, I just compute the losses on the samples I care about, and these are vectors of those losses. And so I have this window of m of these loss vectors, and then I compute the covariance of these, and this is my covariance matrix. Now you can ask, is this actually a covariance matrix? The answer is yes, in a complicated way that I don't really care to explain any deeper than that. And so why do this? And it's because you only need to make n forward passes per checkpoint, plus the cost of the computation of the covariance. So there's no gradient storage, there's no parameter sampling, no backward passes. So like for like n on this range of like 100 to 1,000, this is completely negligible relative to the size of the training step. And in theory, you could like almost completely parallelize this so that you could do it on like relatively large data sets by just like, during training, you offload model parameters somewhere, do this evaluation, and then like at some other step, you reload the model parameters in and do it. Lots of complicated engineering there that I'm not going to do, but somebody might do it. Hello.
What is the passing in Europe? What is the passing in Europe? Those CDs
Yeah, it's SGD like gives the stochasticity that will let you kind of actually make this covariance kind of meaningful. You can do some other tricks to show that like this actually corresponds to sort of a different kind of object that's like related to the NTK, and you can remove like a lot of the covariance junk. But this is like a limiting case. But this is just like a covariance.
Would you expect it to behave the same way if you did like if you had very low step but used Langevin?
Actually, if you have very low step size and use Langevin dynamics, gives you something like really, really nice. It essentially becomes like almost exactly a scaled NTK. If it's like over a very small window.
Does it agree with the data with the information you get from here, or like?
Oh yeah. Broadly speaking, like it sort of should, and there's a sense in which like you can measure this thing instantaneously. Like you can actually just take one window and do this, and it will give you something meaningful. It just is like really sensitive to noise. That's about it. Yes.
On the last slide, you talked about analogies, so like correlation line. Probably slide. But the correlations here are about them. Is there a notion of that?
Is there a notion of like correlation length?
Well, yeah.
Okay, so this is like also a complicated question because the thing that you need to ask then is like, what is the notion of distance between data points? And like my working hypothesis is that it's something like mutual information. But like you can sort of tell immediately that like this is like not a straightforward thing to define. So there's some notion of like correlation length that's very difficult. And sort of like intuitively why this is because you have these like all-to-all couplings from in the data points. And so if you look at kind of what this looks like is like it's sort of this infinite dimensional system because it's like if I have one data point and then like I add one dimension, it connects to another one, and then I add a second dimension, it connects to another one. And so eventually you get something that looks like an infinite dimensional lattice. And so like distance is weird there. This is the best way I can describe it because like really I don't have a good answer for you, so I'm sort of just bullshitting, but like anyway, any other questions? No, we're good.
You'd be like, okay, what should we think of the task as being? Maybe you'll introduce it, but like, can you give like 3 words on what the task, what is being trained at how many layers?
Oh, brother, we're going to look at a couple of them. We're going to look at deep linear networks. We're going to look at induction heads. We're going to look at grokking. We're going to look at emergent misalignment, and then we're going to talk about why doing certain things is harder than others, and why this is a problem actually for almost any method that you could try and use to understand phase transitions. So we'll get there. It's very fun. Okay, so why the training trajectory? Because like it might seem really weird to do, but actually the optimizer is like a natural importance sampler. And so it only really moves along directions that matter for decreasing the loss. So directions with like large gradients are explored, and like basically entirely irrelevant directions are ignored, modulo some details. And so the reason that like why you would do this is like analogous to this thing in chemistry called reaction coordinates. Because like during a reaction, most degrees of freedom are spectators, like a lot of the system isn't doing anything. So you want to study a reaction, you track the sort of parameters, the coordinates that the reaction is actually moving along. And so the optimizer's trajectory, or like decomposition of the trajectory, is like the reaction coordinates for learning. This is kind of the idea. The other thing is I missed a flight and was like super sleep deprived. And it's like, what if this works? So like, what do you do with this object? Like, how do you actually use it? So we have this covariance matrix, and like one of the wonderful lessons of physics is that like you just sort of look at the eigen stuff, and that basically tells you everything. Like, I mean, I come from quantum junk, which is all eigen stuff. I think that quantum's just SVD, basically. Somebody say something? Very good.
It'll be well received.
So we take this thing and we give it the spectral decomposition. So you can ask what the eigenvectors are. this sort of tells you who moves together. So VK is a vector in sample space, right? Its entries sort of tell you how much the sample I participates in the mode K. And so if a group of samples all couple together to like create the same sort of merging capability, they will kind of load onto the same eigenvector. And you could test this. And the eigenvalues, it kind of tells you like the sort of like it's sort of a large values of these eigenvalues mean that these samples losses are fluctuating like a large amplitude, like they're kind of just going really aggressively. So like if all of these eigenvalues are roughly equal, losses are kind of fluctuating independently in many directions. So like nothing coordinated or interesting is really happening. I'll show you some details. So we then define this thing, and we can talk about it more and like the sort of rigorous junk about it kind of at the end. And we call this thing the spectral heat capacity, and it's the variance of the eigenvalues. And it sort of measures whether your eigenvalues are like really spread apart or they're like really bunched together. So a large spectral heat capacity means that the fluctuation structure is sort of anisotropic, like things are sort of fluctuating very differently. And a few modes are like dominating the dynamics.
We should think of this as being much larger than a random. It's like a random matrix is small.
Yeah.
In this intuition. Okay.
Yeah. So the other thing is like in a rigorous way, you can like prove that the spectral heat capacity is like an early warning signal, in that it will spike before a second order transition, or that it will spike with a first order one. And this is sort of like it in some sense, like really what's going on is it detects like different kinds of things. And one of those things is like something that's akin to silent alignment. And the other thing is when like new curvature directions pop up. But we talk about that more at the end if people are interested. The other thing that we introduce that I don't, in the experiments that we go over here, I don't spend that much time on it because it's sort of like, it's interesting, but it's interesting because it helps you do a certain thing. And anyway, this thing that I'm talking about is called the participation ratio, which is the square of the sum of eigenvalues divided by the sum of the eigenvalues squared. And so if your participation ratio is low, this means that like all the loss co-fluctuation is happening in a single direction. So the transition is very localized. And so you have like one coherent group that's sort of being reorganized. And so if your participation ratio is like really big, this means there's sort of multiple directions of reorganization that are sort of happening simultaneously. So this transition is very broad. Like, so like you would expect something that's like a genuine global reorganization of the system to have like a very high participation ratio. Interestingly, you don't see that very often. Most transitions seem to be very local, which is kind of consistent with like the fact that we know that like stuff exists in relatively small portions of the network. And so there's this interesting thing where like temporal ordering matters. So you can have the spectral heat capacity spike before this participation ratio rises. And this is sort of like, you have a narrow bottleneck, and then one mode sort of leads, and then everything broadens. But if you have the participation ratio rise before the spectral heat capacity, many directions are sort of softening simultaneously. And then like the sort of symmetry between these eigenvalues breaks, and one just pulls ahead of all the others. So the participation ratio can increase either before or after the transition. While the spectral heat capacity, it has to increase before or with the transition. So like you can actually have that the PR rises before the SHC, but it won't always do that. So you can't rely on it as an early warning signal.
Do you know how energy? So like right specifics, like right before the PNE, let's get about it.
In some instances, it's like experimentally, we found that there's some instances where it can be somewhat significantly before. And I think that this like empirically depends. Like I think you can slow it down if you like make your learning rate really slow. Sometimes this seems to have something like this sort of effect.
But you have a sense of like what controls this, because right, like you're asking how wide would level your critical region is or something like this.
There's some extent to which. So there's a couple things. So first, the data that you choose for the probe set matters a lot, and like we talk about this more, because if you can't see, like let's say you have a thing that's happening with like a group of samples that aren't really in your probe set, then you're not going to see much of anything. And so like, if you only have a small amount, that would sort of spike that participation ratio. That like it's just not going to be very high. And this is the main control parameter. Like it isn't kind of an interesting question that like we didn't directly explore in this work is like like if you change the sort of parameter, like the learning parameters, how this changes the phase transition structure. Basically just because the thing was like, oh, we could do early warning, like, huzzah, I need to get grants, I'm going to put a preprint out. That's like full transparency. So yeah, this is sort of like a picture. I didn't know how else to like display this, but you sort of see here that you have this like narrow bottleneck, like one mode dominating. So like the thing sort of like, you can imagine kind of flattening, and then you sort of, pull ahead here. This thing is like you have many directions soften, and then eventually one will pull ahead. So this is sort of like the two different behaviors this can have, and like it'll be interesting later to do more research into what's actually driving this. But like, not gonna lie, I don't really know. So this is like meant to be like sort of an intuition on why this variance of lambda is an early warning signal. And that it's sort of the like minimal statistic that distinguishes that the system is just kind of noisy from like the system actually organizing in a meaningful way. Because like isotropic noise, like if all the like losses are sort of just like fluctuating, like in sort of a structureless way, it's not going to produce any variance in these eigenvalues.
I guess you can have this second thing maybe if you like have two circuits that we're learning, but then one of them becomes much better and the other one gets forgotten.
Yeah, this is like the intuition about what's happening, because it seems like really it's like something, there's like this transition where like later in training, I would guess that you would get more of this sort of thing where like you're sort of getting this like softening a bit more, where like you're basically, at that point, it's like you have defects on the circuit that are just slowly getting pruned out. And actually, there's a graph that will show where you can actually see something kind of like this. But anyway, the moment your fluctuations concentrate along a subspace, along a subspace, the eigenvalues separate and this variance will fire. What's the next slide? Okay, yeah, this is just the thing about like the sort of temporal ordering. So you can sort of see here that like this thing is stable, and as it sort of starts to soften, like it starts to like go, you can imagine these things as like getting sort of flattened out. That like they start to soften out and as you sort of approach the phase transition, the spectral heat capacity starts to go up. Now, one of the interesting things you'll sort of see here is like this is the like a Hessian mode, and that this is the spectral heat capacity. So this goes up while this goes down. But so you might say like, why not use the Hessian? Because like in a fundamental way, if you use the Hessian, you can't tell what's changing. Like there's like a sense in which you would not get any information because it has not been realized in like the sort of the space of data points yet. So like this is the same thing as if you tried to look at like a chemical reaction and be like, I know that a critical nucleus is going to form over here. Like you don't, you can't tell, because you don't have a measurement apparatus for that. So now we're going to talk about some experimental results, to sort of show that like this thing does seem to work, and then we'll talk about some shortcomings and some future directions. So this is sort of like on a really simple toy model, just show like the sort of workflow you have with this thing. So here we just have this sort of one-dimension model with a structural coordinate. We give it two phases. And sort of as we move and we sort of track the per sample losses, we have these different groups of data points, group C, group B, and group A. And we can sort of, we compute the losses on these and we track them. And then we make this matrix, which is like our covariance snapshots. And you can see that when the spectral heat capacity spikes, you get that there's this structural reorganization here, like very visible in this guy. And then after it goes away. And this is sort of, the fact that it goes away is like a reflection of the fact that like the directions on which it was reorganizing are no longer like actively being explored. So if you were to do something with like instead of following, like doing the sampling during training that I'm doing, if you were to do something like the Bayesian posterior sampling or whatever, you would expect that these things would still show up there because it would be kind of aware that those directions exist. But like here we learn the thing, and then like the active directions of SGD just aren't going to try and like for at that moment it's like, well, I've learned this, I don't need to explore that direction anymore until something changes and it starts to explore that direction again. So yes, this is the basic idea.
Okay, so you mentioned like if you change the sampling distribution to the Bayesian posterior, is that what changes?
Oh, it's basically, so when the Bayesian posterior will remember the direction, the things that you've learned. So like you'd have some direction, imagine like it flattens out, and then that direction just stays flat. Well, gradient descent, unless you have like weight decay or something, but like just ignoring that, like isn't going to move along that direction very much. So this thing just isn't going to pick up on it anymore. It's like, well, I've learned this. And so if you do the whole Bayesian posterior sampling, you're still sort of aware that that's there. But in this case, it's like Bayesian posterior sampling is expensive. So we just try and remember what was learned in some other way. Yes. So the first experiment is with deep linear networks. And I think a bunch of people have talked about silent alignment already, so I don't really want to rehash it too much, but essentially you have a deep linear network will align the singular vectors of its weights with the singular vectors of the teacher matrix in a particular sequential way with like this wonderful, like all this is very, very nice theory. But the important thing is that like once it sort of aligns on a direction, it'll amplify along that direction, which sounds a lot like phenomenologically a lot like this nucleation thing. So you can use this as like this sort of like unit test, because you kind of know exactly when the structural change happens, and the spectral heat capacity, you kind of know that it should spike like with the silent alignment. You can detect the silent alignment and it should spike there. It should not really spike like significantly before or after. So you can check that this thing kind of works. So here, there's actually 3 modes. One of them is slightly hidden, but you can sort of see that like when we look at the sort of per mode joint alignment versus the spectral heat capacity, you can see that like it spikes, like broadly speaking, within a very narrow window of these things. And we do this over like a whole bunch of like, like random seeds and sort of different settings. And this is basically always the case. So like this seems to be like, yeah, this thing does the thing that we say it does. But like deep linear networks are like far too simple for me to like say that this is like super meaningful. So we got to go, yes.
Which curve package has seen?
This guy. He, yeah, this is the red is the spectral heat capacity. And then these guys are the modes. There's a secret third mode, which corresponds to this guy. Yeah. So this is cool. This is like, okay, it does the thing that I think that it should do in this case. Very good. Yes.
Like, there is a lot of fun with sacks, right? So when the 2-layer linear network.
That's what this is about, yeah.
Yeah. Unless you take some other limit, you don't have a phase transition there, right?
Well, okay, so there's a thing about like what do you mean by a phase transition? Right, like it's just so the thing is like I think that this is like a common thing where people are like, oh, this thing isn't a phase transition, but like lots of things that people say that aren't phase transitions, like are phase transitions. Like people are like, oh, you need to go to the thermodynamic limit to have phase transitions. You don't. You just study the Li-Yang zeros or whatever. But like in this instance, it's not a phase transition because it's a metastable state to metastable state thing, but the system is reorganizing. And the whole thing that I want to detect is like, we know that this thing aligns and then amplifies. So I want to detect this alignment. And like, this looks like a nucleation event. And so if it like looks like a duck, quacks like a duck, it's a duck,
Yes, they're just saying there's like one eigenvalue that suddenly becomes much bigger than the others associated with learning.
Yes. Yeah.
But yeah.
Yeah. Yes.
So the spectral peak capacity is supposed to be like an early warning that's before
the thing is,
It's like after if the sum.
this is a unit test because these things you should not pick up on significantly before. This is silent alignment. So in theory, like this is like a validation of the limits of this theory, because it shouldn't really be able to meaningfully detect anything before silent alignment happens. Because by definition, in some sense, like yeah, we might know this is going to happen because we a priori have a lot of knowledge about the system, and in some sense we have infinite knowledge about this system. So like, yeah, like we might know that it's when it's supposed to spike, but this thing can't see that. So when it does this alignment, that's when it should spike, because this is like a first order phase transition.
My guess here, like what I would guess is happening here is actually different from like the things that I thought you're and maybe different from what will be happening in future and the other, because here there's actually nothing really thermodynamic happening.
There's no thermodynamics in any of this.
This is just taking a derivative. This is just saying the derivative of this mode is becoming large, and therefore the variance in a window.
Yeah. This is why it's like kind of a unit test, because we sort of know this. And so if this thing...
But it's not saying this direction is fluctuating more, it's saying this direction is changing more. The derivative is higher rather than the fluctuation.
Well, the thing is that the fluctuations, like the idea is the fluctuations encode that information. This is sort of the trick. And like when I talk about like the formal thing that you can show about why this works, it's basically like when you dig into it and you look at it, it's actually that like it's picking up gradient signal. So explicitly, like what's happening is this thing's actually sensitive to if gradients, like a line, it will just pick up on that. So like, anyway, so this is basically was like a valid, yes.
So it kind of affects like the early mass of it. Here it's like too late to try.
No, so this is not supposed to be early. The fact that this is not early is like what you would expect. This is a first order phase transition. Like this thing should, because the loss, like the loss in the Sachs paper doesn't decrease until after silent alignment, right?
Decrease.
It doesn't decrease. Like this is what silent alignment is. Like
talking silent alignment.
What?
Sachs paper.
No, it's Jaco. Sorry, but like the whole Jaco 2022.
Alex is silent alignment.
What?
Alex is silent alignment.
I'm familiar with the, like I'm looking at the Jaco paper, but this is like it's just the singular vectors of the student matrix aligning with the singular vectors of the teacher matrix, and then they amplify. So like before they align, the loss doesn't appreciably decrease, and so when they align, the loss starts to decrease.
So regardless, wouldn't you say that like you kind of have the capability once the singular body is already up, and then here like it's on, like wouldn't then?
Well, I think part of this is the fact that like. This is a first order phase transition. Like you just can't detect it early. Like the best you can hope to do is this. Like you can't detect this early without a priori knowledge of the system, because then it would be like it would be the equivalent of being able to detect a nucleation from just thermal fluctuations. Like this is just like not really feasible unless there's like some sort of like particular properties of the nucleus. But like anyway. There's more interesting things than the deep linear network case. This is sort of meant to be like, here's the thing that tells me that the theory does what I would expect it to do in this case. So blah, blah, blah. This is all the stuff we just talked about. And sort of you can see here that like essentially the time, like right here, the timing is correct. The detection occurs like kind of concurrently with this first order like transition, which is what the theory would tell you. And you can explicitly work this out. Like you can explicitly derive the fact that like with in the DLN case, that the spectral heat capacity has to spike when the silent alignment happens. Like this is like you can prove this rigorously.
Yeah.
So yeah, the next one to test is next token prediction over like random token sequences. So this is induction head formation. So like, you have some, sequence, like random tokens, and then there's some bigram that appears. And then so when you give it to the thing, it learns like, oh, I've seen AB previously in my context, so if I see A again, I'm going to guess B. And so we sort of know that this emerges as sort of a sharp phase transition where attention patterns suddenly reorganize. So how do we test this? So we have half the probes are repeated sequences. So every bigram in the first half reappears in the second, so the induction circuit can exploit them. The other half are random sequences, so they benefit from n-gram statistics, which we know were learned earlier, but not from the same induction mechanism. And so unlike the deep linear network, where the inductions where like we sort of know what the timing is, the induction heads are like a real capability in a nonlinear model. So the spectral heat capacity should spike before or concurrently with the jump in the induction head score. And so in the paper, we do check this. It corresponds to known phase structure. This is just a thing to say that like we do a bunch of other stuff in the paper that isn't in here. But you can actually see here that we get three sort of things going on here. So we get this spike, we get this spike, and then we get this here. So these things all actually correspond to 3 different sort of phases of the model. So we basically are able to go in and look at sort of what part of the data has, like what behavior has changed. So when you look at this thing spikes because the model starts to understand the n-gram statistics, and this is sort of a thing. I think that actually this was a... Yeah, well, in this case, it's just like random stuff, so it's just sort of like bigram statistics.
Bigrams are linear until they get long first.
What?
Bigrams are linear long first.
Yes. So this is the idea. So this spikes with this, and then you sort of see that like it kind of flattens out, and then before the induction head scores increase, this thing goes up, and then it goes back down. And so this corresponds, you can check this, that this is actually happens when it starts to figure out that there's like, it's just to actually get induction head structure. And then you can ask like, what the hell is going on here? This is actually I found this quite interesting. So after it learns that and this, the only thing left to try to do is memorize the training samples. And so what happens is the system basically will like memorize things and then break them off repeatedly. And so what you get is that like you sort of have this like phase transitions are everywhere picture because parts of the model keep reorganizing to just fit to different parts of the data. And like you can check this all with by like looking at this, like certain scores, what have you. But so this sort of like kind of matches the structure that we know is here. And then this thing I did not know was there, but then we went in and probed it, and that is the thing that's going on. So here's the second piece of evidence. This actually does something like early detection of phase transitions. I got flip back over here. Okay, so the other one is that's obvious to check is like the Grokking modular arithmetic. So we just train an MLP on modular division, mod 97. And so like, yeah, just memorizes the training set, and then it generalizes. And we sort of know what the circuit does because it implements a discrete Fourier transform. So here's the probe set design. We pick 150 training samples and 150 test samples. And so we kind of know that like the memorization circuit is kind of like a lookup table, which affects the training samples, but tells us really nothing about the test samples. And the generalizing circuit exploits the Fourier structure that's like kind of just shared across all of its inputs. So like we kind of are like, we know that there should be some sort of difference between how the spectral heat capacity behaves on the training data versus on the sort of testing data. So we split these out. So we have a train block spectral heat capacity and a test block spectral heat capacity. And we investigate these. And then we also like look at like the top eigenvectors to be like, oh, this is doing the Fourier thing, blah, 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 just to confirm that it like picks up on the stuff that's known about in Grokking. But we go here, you can see that if you go to the train only covariance block, this thing sort of and this happens very, very early on where it starts to actually sort of learn the train, like it learns the training distribution. So this thing spikes, but you'll notice that actually this is only for test samples. This thing also spikes. And then as it sort of approaches where the sort of accuracy goes up, this thing spikes again. And like, okay, well, why is this interesting? And it's because you would not expect that the loss fluctuations within the test set should really be affected at all. It hasn't seen any of them. But actually there's a relatively large co-fluctuation in there that produces a noticeable spike, which is somewhat counterintuitive.
No, this is just GP. So GP. So if you have.
Yeah, it's lazy to rich.
Yeah. So in this case you have 90 samples. So if you learn all of n squared, so which is like not that far from, then you will actually learn in GP. Yeah,
I'm kind of avoiding talking about the fact that this is doing like this tells a lazy to rich story.
It actually does do a little bit of generalization if you're close to the full data set.
Yeah. So this is like there's a very nice like lazy to rich story to tell with all this stuff. But so the sort of final thing is like the stress test, which is we train like a low rank adapter on Quen 2.5 using this bad medical advice data set. And we sort of kind of just produce this very subtle behavioral shift, which is like barely a 20% like alignment drop. And this occurs actually within the first like 5 to 10 steps of training. So it's like quite hard to isolate. And so the idea is that this sort of is like a stress test of this method. Now, what is the thing? So we designed this probe set. And the idea is like this probe set has a couple of things in it. It has benign capabilities. some sort of boundary ambiguous ones. So you might say something like, I want to cut the head off of broccoli. Like, it's not the same as cutting the head off of a dude, but like, you know, some of these like models that are used to sort of classify things as like good or bad, like we'll be like, hey, that's bad. Don't cut the head off of stuff. The other one is like we have medical advice that's sort of similar to the training data. And then we have like these various alignment probes. So the transition happens in very few steps, which is sort of not enough samples necessarily to do this dynamical thing. You technically can, as Giorgio put me on, that you can just do this thing at a single spike, but it could be very noisy. So instead, we just do like a little Gaussian perturbation on the low rank weights, which actually you can blend this sampling into the training sampling in like a coherent way if you wanted to. That turns out we didn't need to. So if you look at this, we just sort of compute the like alignment scores that they compute in the model organisms of emergent misalignment paper. And you see that like really early on, you get this big spike in the eigenvalue variance, the spectral heat capacity. And right after you get the spike, the coherence score goes down, which isn't desirable, but the alignment score goes down. And then it's sort of like, if you just keep training it for a really long time, it kind of just stays around there. This is actually like a really, really subtle change in its behavior. And it's really only reflected in a small amount of samples. And actually we can see this when we do this decomposition. So we decompose this full spectral heat capacity into alignment probes. The sort of, like these are basically all the ones from this paper, like they get these different forms. So we have these various ones, like these free-form ones, these ones that are JSON formatted, these ones with a very specific templating, benign capabilities, these boundary ambiguous ones, and the medical advice. And you'll notice that the one that actually dominates these JSON alignment probes. They pick up on the fact that this thing is undergoing some sort of like transition in its behavior before it actually undergoes that transition. You pick up this up a little bit in the alignment probes. The interesting thing is that this thing's trained on bad medical advice, so I would expect that actually its behavior on medical advice should be the thing that tells you this, but it's not. So this thing has somehow, like, basically is sort of like picking up on like a shift in like sort of a different data distribution than the one that's actually sort of being trained on, which I think is quite interesting. What is the next thing? The discussion and the conclusion. So like, one of the things that I sort of haven't really talked about, and this is like not a unique thing to this 2RDM, and I think that this is a thing that we kind of always like brush under the surface, is that like if you're trying to detect any sort of phase transition behavioral thing, you need to choose the sort of right probe set. Because like in the sort of dumbest way of putting this, you can't tell if the model has a behavior if you just do not have the tool to measure that behavior. Like you could not hope to go into weight space and be like, I know exactly what this weight thing looks like. Like this is just like incredibly hard. So in all the settings here, the thing that like is going on while we get these like very, very nice pictures is because this sort of like randomly sampling from the data set captures a lot of the variance. But as you can sort of see in this like emergent misalignment picture where I do this like very specific probe set selection, like that just wouldn't work. If I just selected from like the pile or whatever, like I probably wouldn't pick up on anything. So like you kind of need to be able to like pick the right like sort of probe set. And there's some like partial mitigation built into this. And like, if you had the ability to do like, 100,000 samples, you can use the participation ratio to identify which samples are participating in a transition. And you can then restrict diagnostics to like an active submatrix. This is like in quantum chemistry, this is like active subspace methods basically. But like if no probes that you have coupled to the transition in like the spectral heat capacity, you won't see it, and neither will any other thing that you could do. Like you just need the right probe set. So this is like a thing where we kind of can take lessons from a field of physics that I think is like not talked about much in this space, which is quantum chemistry, because this is like identical to the basis set selection in quantum chemistry. Because like really what you do is you have like some, like you have a Hamiltonian that like operates on like this sort of infinite dimensional Hilbert space where all your molecular orbitals live. But you can't run this thing on like this infinite sort of like the basis of an infinite dimensional Hilbert space. So you truncate it down, right? Like you make a choice of basis, And you sort of say, these are good enough for my purpose. But if you select like the wrong ones during like a bond breaking event, you just don't see the bond break. So like, we kind of need to do something similar where we sort of say, here's some principled methods for finding out what probes are actually going to probe the behavior that we care about. This is a highly non-trivial problem, but like we can sort of like try and take some inspiration. So the future idea is like, we can sort of look at the decades of research in quantum chemistry, where you have like these systematic basis hierarchies. So you have like your basic like Gaussian basis, and you sort of have all these modifications on top of it, like couple clusters, blah, blah, blah. And each level kind of adds functions to resolve specific physics. And this suggests something like a similar hierarchy for probe sets. So you might take like some core sample, which is just like a uniform sample of the distribution. You might take polarization samples, which are sort of near category boundaries, which are not obvious, like what the sort of like discrete categorical structure is. You kind of want to take some diffuse samples, which are sort of at a distribution, tail samples, adversarial samples. And then you want to take like some task-specific ones, which are targeted probes for like known risks that you care about, like learning to do like really crazy hacking or something. So the natural next step in this sort of line of research is designing these sort of principled probe sets. Anyway, this is the conclusion. You can read the paper if you want, and you can ask me questions. I'm done now. Bye.